In this set of lecture notes, we will cover multiple linear regression. Let's take a look at the multiple linear regression model relating a number of independent variables to a dependent variable y. Just like in the simple linear regression model, the outcome variable has to be continuous and is predicted using an equation of a straight line. This equation, this regression equation, is built based on sample data for the variables y and x. And again, in multiple linear regression, we have several independent variables as opposed to only one. That was the case for simple linear regression. Just like in simple linear regression, in multiple linear regression, we use the least squares method, LSM, to estimate the regression coefficients associated with the slope of each independent variable and intercept. So the estimated model or prediction equation would be very similar to a simple linear regression model, except that besides the intercept and the slope of one independent variable, we now have multiple slopes, each one associated with a specific independent variable. And of course, E, which stands for residual, the amount of unexplained variance in the model. The model fitted in multiple regression is more complicated though, but the basic principle is the same as in simple linear regression. That is, the goal is to find the linear combination of predictors that correlates maximally with the outcome variable. Let's take a look at the parameter interpretation. The outcome variable in multiple regression can be expressed as the expected value or the mean value of y, and that is denoted by E of y, or again as the expected value of y equals the intercept plus the slopes of each of the associated independent variables. And again, when the values of all of those independent variables are 0, then the expected value of y, or the mean value of y, equals the value of the intercept, beta 0. Now, let's suppose that in a multiple linear regression model with two independent variables, x1 equals 0 and x2 equals 0, which means that the values of the two independent variables is 0, then you can see here that once you set those values to 0, the mean value of the y will equal that of the intercept, which is beta 0. Continuing with the parameter interpretation, we are now taking a look at the regression coefficients for each of the slope associated with each independent variable. So we call the B1, B2, or BK, which are essentially the estimates of the beta 1, beta 2, beta 3, all the way to beta k. These slopes are now called partial regression coefficients. So controlling for other predictors in the model, there is a linear relationship between the expected value of y and x1 with slope b1. So let's look at an example where we have two independent variables again, right? So we will have x1 associated with a slope of b1 and x2, independent variable 2, associated with a slope of b2. If x1 goes up 1 unit with x2 held constant, then the change in the expected value of y is expressed as the difference between the two terms we have listed here below, where basically one term indicates the intercept plus beta 1 times, in parentheses, x1 plus 1 plus b2 x2, close the bracket, minus, open the brackets, and place in the expected value of y equals the slope of beta 1. So The key here to remember is that we have partial regression coefficients because we now have to take the amount of variance, the effect that another independent variable has on the outcome, while we're holding constant the effect of the other independent variable, let's say x2, on the outcome. So that way we can estimate the true effect of a particular independent variable on the outcome while we're controlling or holding constant the rest of the independent variables in the model. As we mentioned earlier, we use the least squares method to estimate the regression coefficients associated with the slope of each independent variable and intercept. So the prediction equation that estimates the multiple regression equation is given either, can be expressed either as an expected value or just simply the mean of the dependent variable, which equals the intercept plus each of the slope associated with each of the independent variables. Again, the goal of the LSM is to, in estimating the values of the coefficients, is to minimize the sum of squared errors. Basically the SSC, which is our unexplained variance in the model. The multiple regression model has residuals that measure prediction errors. For a subject with predicted response y hat and observed response of y, the residual again is the difference between the observed and the predicted value for y. So again, just like in a linear regression model, the sum of squared errors is just simply the sum of the square differences between the observed and the predicted values of y. And it is extremely important that the residuals are computed for a number of reasons. Just like in the simple linear regression case, we will use these to test the assumptions. Just like in the simple linear regression model, we have total variation, we have explained and unexplained variance. And as we indicated earlier, the unexplained variance is given by SSE, the sum of squared errors. And from that, we can estimate the mean squared error, which is essentially the residual variance. And finally, we can estimate the residual standard deviation. We also have explained variation, which is the SSR, which is the regression sum of squares. There are a number of limitations associated with the multiple regression model. In interpreting partial regression coefficients in observational studies, we need to be cautious not to regard the estimated effects as implying causal relations. Association never implies causation. This is extremely important as a number of people might interpret significant findings as a cause and effect, when this should not be the case for any of studies that conduct regression analysis like this one. You might find associations, but again, these associations do not imply causation. Also, a multiple regression model has a structural limitation. So it assumes that the slope of the partial relationship between y and each independent variable is identical for all combinations of values of the other independent variables. And this is something we need to keep in mind. So let's look at an example that has to do with mental impairment. Let's suppose we have a study where the sample size is 40 subjects, and we would like to examine the effects of adverse life events in previous 3 years and socioeconomic status or mental impairment. Let's figure out what are our variables here. Which variables are the independent versus dependent? The dependent variable is mental impairment, because it summarizes the extent of psychiatric symptoms, including aspects of anxiety and depression, based on questions in a health opinion survey. So the values of this mental impairment variable, let's say, may range from 17 to 41 in this particular sample, where the mean is 27 and the standard deviation is 5. Our two independent variables include life events, which is measured as a score ranging from 0 to 100. So it's a score variable, and it includes adverse life events in previous 3 years. For this sample of 40 subjects, the sample mean is 44 and the standard deviation is 23. Our second variable is socioeconomic status, and this is a composite index variable based on occupation, income, and education. So 3 variables are taken into consideration when calculating socioeconomic status. This variable also ranges from 0 to 100, where the sample mean is 57 and the standard deviation is 25. So looking at these 3 variables, we notice that all 3 are continuous variables. The outcome variable, mental impairment, obviously needs to be continuous if we want to run multiple linear regression. But certainly x1 and x2, the 2 independent variables, are continuous here as well. Let's continue with the mental impairment study. Let's suppose that we conduct multiple linear regression, and the regression equation for mental impairment is as follows. Y hat, which is the outcome variable mental impairment, equals 28.23, which is our intercept, plus 0.103 x1. 0.103 is the slope associated with the independent variable life events, minus 0.097 x2. 0.097 is the slope associated with the independent variable SES, socioeconomic status. SES stands for socioeconomic status. Now, let's see how we interpret these regression coefficients. In other words, what do these numbers mean? So let's interpret the regression coefficient associated with life events. So we would say the predicted mental impairment value increases by 0.103 for each 1 unit increase in life events, controlling for SES or socioeconomic status. Now, looking at the predicted mental impairment value for the second independent variable, we would say that mental impairment decreases by 0.097 for each 1 unit increase in socioeconomic status, controlling for life events. And we say decreases because there is a negative association, as it is reflected by the negative sign associated with the slope of SES between SES and mental impairment. Now that we have the regression equation, we can actually compute the values of a value of y for specific values of x1 and x2. So let's suppose that a subject in the data file has the following observed values: y equals 33, x1 equals 45, which again x1 is for adverse life events, and 45 here is close to the average value for the sample. And this subject has a value for socioeconomic status of 55, which is again near the mean if you recall the information from the previous slide. So this subject then has a predicted mental impairment score of, then you just simply take the regression equation shown in the previous slide and place the values of 45 associated with the slope for adverse events, and then place the value of 55 next to the slope associated with the SES, and that will give you a predicted value of 27.5. And that 27.5 is also close to the average value for mental impairment for the entire sample. So if we wanted to compute the residual, the prediction error, as we call it, for this particular subject, we simply take the predicted score for mental impairment and subtract it from 33. 33 is again the observed value for the subject, and that gives you 5.5. So what does this mean? This person has a mental impairment 5.5 higher than predicted given his or her values of life events and socioeconomic status. Let's take a look at the coefficient of multiple determination in multiple linear regression. Again, just like in simple linear regression, R squared, which we call the coefficient of multiple determination here, is the proportion of variance in the outcome variable explained by the regression model. And it's computed by simply subtracting the SSE, the sum of squared errors, from the total sum of squares divided by the total sum of squares. So the numerator of R squared, which is basically the difference between TSS, total sum of squares, and the sum of squares due to the errors, we call this the regression sum of squares. This represents the variability in Y explained by the model. The properties of R squared include the fact that the R squared is a positive value, so it's going to be between 0 and 1, including 0 and 1, and obviously it cannot be negative. The larger the value of R squared, the better the set of explanatory variables predict Y. Again, explanatory variables here are the independent variables. When R squared equals 1, then the sum of squared error, or the residuals here, equals 0. That means it's a great model in terms of predicting your dependent variable. When R squared equals 0, that means essentially that the correlation between your dependent variable and each predictor variable is extremely low, around 0. And essentially this means that this is not really a good model. R squared cannot decrease when predictors are added to the model. Okay, and basically the sample R squared tends to be a biased estimate upwards of population value of R squared, more so for smaller sample sizes. That means when we say upwards, it means that every time we add a variable into the model, even if the variable is not a good predictor of the dependent variable, the R squared will tend to increase. So because of that, we have the statistical software that we use for statistical analysis report, besides the actual value of R squared, it also reports the adjusted R squared, which is a less biased estimate. And so in multiple linear regression, we like to use the adjusted R squared instead of just the R squared, simply because of this bias, upwards bias. Going back to the mental health impairment example, let's suppose that the value for the R squared is 0.34. This means that 34% of the variation in mental impairment is explained by life events and socioeconomic status. So the multiple correlation can be found by simply taking the square root of 0.34, and that will give you 0.55. And what that means is, it means that the correlation between the 40 values of Y, which is the sample size there, right? 40 values of Y, and the 40 corresponding predicted Y values from the prediction equation for the multiple regression model is 0.58. To test the overall significance of the regression model, we use a hypothesis test that includes hypothesis, the null hypothesis, that indicates that all of the slopes associated with the independent variables equal 0, that is, y, the dependent variable, is independent of all the explanatory or independent variables, or you can say that the independent variables have no effect on y. And the alternative hypothesis would say that at least one independent variable has an effect on y, controlling for the others in the model. So beta I, at least one of the slopes in the model will be different than 0, which means it will have an effect on the dependent variable. This hypothesis can be tested using the F distribution. So we have what we call the F test for the entire model, which is expressed as the ratio test, where we have the explained variation divided by k, degrees of freedom, over the unexplained variation, which is divided by n minus parentheses k plus 1, which is the degrees of freedom associated with the unexplained variation. So the F test we saw in the previous slide can also be expressed as r squared over k. K, again, is the degrees of freedom, and it depends on the number of independent variables in the regression model. And r squared stands for explained variance or explained variation over the amount of unexplained variation, 1 minus r squared divided by its degrees of freedom. A larger value for r gives larger F test statistic, which means stronger evidence against the null hypothesis, which means that we're more likely to reject the null hypothesis and therefore conclude that we have a strong and good regression model, meaning the variables in the regression model are significant, more likely significant predictors of the outcome, or they're good predictors of the outcome variable. So we can reject the null hypothesis in favor of the alternative hypothesis if basically the p-value is less or equal to the level of significance alpha value. So let's take a look at the properties of the F distribution. The F distribution can take only non-negative values. It is skewed to the right. The mean is approximately equal to 1, closer to 1 when the sample size is large, and the exact shape of the distribution depends on 2 degrees of freedom. Basically, it depends on the one set of degrees of freedom, which is equal to k, and this is the number of explanatory variables in the model, and then the second degrees of freedom, which is n minus parentheses k plus 1. So basically the sample size minus the number of independent variables in the model plus 1. Let's go back to the example of mental impairment. And the question is mental impairment independent of life events and SES? So the null hypothesis would say that the dependent variable has nothing to do or is not associated or it is independent of x1 and x2, basically life events and socioeconomic status. The alternative hypothesis, though, would say that either the slope 1, meaning the slope associated with the life events, is not equal to 0, or that the slope of the second variable, socioeconomic status, does not equal 0, or both do not equal 0. To test this, we use again the F test that we covered just a few minutes ago. And when we calculate the F test based on the sample data, we have a value of 9.5. And this value of 9.5 for an F test yields a p-value of 0.001. It's a very small p-value. And the conclusion from this is that we would reject the null hypothesis since the p-value is much smaller than 0.05. Again, 0.05 is our significance level, and conclude that mental impairment is not independent of life events and socioeconomic status, or that the overall model predicts significantly the outcome. So at this stage, all we're concluding is that the overall model is a good one because it predicts the outcome variable. However, to examine the significance of each slope, we would have to look at the regression coefficients and the associated t-test and p-value for each one of those. So to test the significance of each independent variable, just like in simple linear regression model, we can use the t-test, and we set up the hypothesis either as non-directional, where basically the slope does not equal 0, or we can have the alternative hypothesis being directional, where the slope can be positive or negative. Usually we do a two-tail test, but if we know what the association might be between the dependent and independent variable, then we can have a directional hypothesis. Essentially, we reject the null hypothesis, which states that the slope equals 0 at a specified alpha level of significance, usually at 0.05, if and only if the appropriate rejection point condition holds, or equivalently if the corresponding p-value is less than alpha. Again, we use the p-value method rather than the rejection region method, and we simply compare the computed p-value to the alpha value that we set usually at 0.05. So let's take a look at the example of mental impairment and the effects of SES and adverse life events on this dependent variable. When we examine the effect of SES on mental impairment, we'll set out the hypothesis as follows. The null hypothesis would say that SES has no effect on mental impairment, meaning beta 0, the slope, equals 0. The alternative hypothesis would say that the slope, beta 0, does not equal 0. That means that socioeconomic status, or SES, has a significant effect on mental impairment, or that SES is a significant predictor of mental impairment. Let's suppose that we do the analysis and the statistical software reports a p-value of 0.002, which is obviously less than alpha. This means that we can reject the null hypothesis and conclude that there is very strong evidence that SES has a negative effect on mental impairment, controlling for life events, or that SES has a significant effect on mental impairment, controlling for life events. We know that this is a negative effect because we already covered the regression equation, and we saw that the regression coefficient associated with SES was negative, indicating a negative association between socioeconomic status and mental impairment. In regards to the effect of adverse life events on mental impairment, you set up the hypothesis in a similar manner, where simply the null would say that adverse life events has no effect on mental impairment versus beta 1 being different than 0, which indicates that adverse life events has a significant effect on mental impairment. When we test this hypothesis, we obtain a p-value of 0.003, which again is much less than 0.05. Indicating that life events has a significant effect on mental impairment. And specifically, this is a positive effect, since we already know that the regression coefficient for this particular variable was positive. Now, we can say that life events has a significant positive effect on mental impairment, controlling for SES. That means holding constant the effect of SES, we can truly say that this particular variable, adverse life events, has or is a strong predictor of mental impairment, or that it has a significant effect on mental impairment. The assumptions for the multiple linear regression model include that the relationship between y and x is linear, the dependent variable has to be continuous, the residual term, again, is normally distributed for each fitted value of the independent variable x, and the variance is constant. Basically, the spread of the residual terms should be the same whatever the value of x. In other words, the residual should not spread out more or less when x increases. So we have homoscedasticity. And we will examine these assumptions in a different set of lecture notes.